Alright, lock in people. Today we're going to be speedrunning through the first module of Year 11 Chemistry, Properties and Structure of Matter. We'll start with a review of basic concepts before getting into properties of matter, atomic structure, periodicity, chemical bonding, and finally into molecular forces and allotropy. Got it? Let's go. So first, we have mixtures and pure substances, classifications which apply to all substances. Pure substances are uncontaminated and uniform throughout, whereas mixtures or impure substances are contaminated with bits of other observable substances in them. We can then categorize pure substances into compounds and elements. Elements are substances which can't be turned into simpler substances, whereas compounds can, being broken down into elements which are bound uniformly to form a compound substance. This will become more important later. Next, we have physical states, or states of matter, your typical solid, liquid, and gas. You can turn solid to liquid via melting or fusion, liquid to solid through solidification or freezing, liquid to gas through boiling or evaporation, gas to liquid via condensation or liquefaction, and solid to gas through sublimation. Solutions and suspensions. A solution is a homogeneous mixture which has particles within it that aren't bonded like a compound but are so small that you can't see them. The dissolved substance is called the solute and the liquid is the solvent, whereas a suspension is a heterogeneous mixture where the particles are big enough to be seen. Now let's look at physical and chemical changes. Physical changes are when no new substance is formed, typically a change just between physical states. Chemical changes or chemical reactions are when at least one new substance is formed. In a chemical reaction, the starting substances are called reactants and what results are called the products. Particle nature of matter. All matter is made of particles. In solids, they're in tight and rigid array. In liquid, they're less orderly and can move more freely. In gas, the particles are well separated and can move much more. These natures all contribute to the physical state's properties in fairly obvious ways. Atoms are the simplest particles representing individual elements. Molecules are groups of bound atoms, being the particles in compound substances. Molecules with two atoms in them are called diatomic molecules, with one atom are monatomic. Ions are atoms and molecules which have either a positive or negative charge. These ions can be bonded together with oppositely charged ion in ionic lattices to form ionic compounds. Positive ions are called cations and negative ions are anions. Symbols and formula. Elements are drawn as one or two letters, be it O for oxygen or Na for sodium, and then compounds are written together with the subscript numbers representing how many of each element there are in the molecule or the ratio of them. Sodium chloride becomes NaCl or H2O for water, with two hydrogen atoms and one oxygen atom. Chapter 2. Properties of matter. Physical properties of a substance are its observable characteristics such as boiling or melting point, whereas chemical properties are stuff to do with chemical change under various conditions such as volatility or reactivity with water. Physical properties can be used to separate mixtures. Filtration to separate by physical state between liquids and solids. Adding a solvent then filtering can be used to separate two solids by solubility. Heating can separate a mixture of two liquids by boiling point. Boiling/evaporation to separate a solute from a solvent. Distillation is the separation by boiling point, but you use a still head and condenser to retain the liquid first to boil, called the distillate. Decanting can be used to separate a liquid from sediment. Separating two immiscible liquids can be done with a separating funnel, which has both a resealable top and bottom because immiscible liquids don't mix into a homogeneous mixture, think oil and water. Gravimetric analysis. This is determining the masses of substances present in a sample of whatever matter you have. Percentage composition is the ratio of pure substances present in a sample, pure substances being either elements or compounds. A survey of the elements. Most elements occur as compounds naturally because over time, elements will eventually have to react to become more stable. Metals are elements which are solid at room temperature, lustrous, conductive, malleable, and ductile. Non-metals are generally dull, poor conductors, not malleable, and solid or gas at room temperature. Semi-metals are elements with properties of both metals and non-metals. The periodic table. A chart that organizes all 118 elements. Columns are called groups which have similar chemical properties. Groups 1, 2, and 13 to 18 are main groups, whilst groups 3 to 12 are transitional elements. Horizontal rows are called periods labeled from 1 to 7. Metals are in the top right, separated by a diagonal border of semimetals. Chapter 3: Atomic Structure. An atom has protons, neutrons, and electrons. The protons and neutrons are in the nucleus, each with an atomic weight of 1, having a positive and neutral charge respectively. Electrons exist around the nucleus in what is called an electron cloud. They have a negligible atomic weight and have a negative charge. The atomic number is the number of protons in an atom, which is also equal to the number of electrons. Isotopes are atoms of the same element with different numbers of neutrons in the nucleus. The chemical properties don't change, but the physical ones alter slightly. Relative abundance is the percentage of an isotope that is naturally occurring. Unstable isotopes are those which spontaneously emit radiation because the gravitational force of the nucleus outweighs the electrostatic force, making the atom unstable. They emit alpha rays in the case of there being helium atoms worth of extra protons and neutrons in the atom, beta rays when there are extra electrons, gamma rays when there is electromagnetic radiation. A nuclear equation puts the emission of radiation into a number as we see the helium atom exit the unstable uranium isotope, leaving behind a thorium atom, that being an example of alpha radiation. The half-life is the amount of time it takes for an atom to lose half its mass in the process of radioactive decay. Energy levels for electrons. Electrons have a set number of energy levels, from first to second to third, etc. Energy levels refers to the number of electron shells in an atom. Reactivity is caused by an atom's tendency to gain or lose electrons to become more stable. That is, gaining or losing valence electrons on the outermost shell to have a full outer shell. This is how ionic bonds are formed. The periodic table again. Every element in a group has the same number of valence electrons. Hence, they react similarly. Every element in a period has the same number of electron shells. Orbitals and sublevels. Orbitals are the volume of space around the nucleus through which one or two electrons move. The first energy level has one s orbital, called 1s, and the second energy level has a larger s orbital, called 2s, and 3p orbitals, called 2p. Then the third energy level has everything the second has with an additional 5 d orbitals, called 3d. After that comes the fourth energy level with everything the third level has with an additional 7 f orbitals. Hence, each energy level has up to 4 sublevels. Sublevels referring to the layers of orbitals s, p, d, and f respectively. Orbital notation is how we write out the electron configuration of an atom with more complexity. Take neon with a configuration of 2a. It has 2 electrons in the 1s sublevel shown in the first term and superscript. Then another 2 in the 2s sublevel with the last 6 in the 2p sublevel, as once again indicated in the superscript. Atomic spectroscopy. Atoms themselves don't emit light, but can do so if given extra energy. If heated to over 1500 degrees Celsius, electrons get excited and rise to higher energy levels, causing the emission of either ultraviolet or infrared radiation. This is called the excited state. And the ground state is when there is no energy, and spectroscopy is the study of this light emission. Flame tests. By lighting a flame to different elements, we can see what properties they convey upon going from ground to excited state. These can be distinctive colors because light is being emitted at a constant frequency due to the consistent electron transition of the atom. Chapter 4: Periodicity. Periodicity is the recurrence of events in regular patterns. The periodic law is that properties of elements vary periodically, hence we get groups with similar patterns. Atomic radius, the distance from the valence shell to the nucleus. This decreases from left to right and increases from top to bottom. First, ionization energy, the energy required to remove an electron from a neutral gaseous form of the element. This increases from left to right and decreases from top to bottom, inverse to atomic radius. Reactivity with water, pretty self-explanatory, increases from top to bottom and decreases from left to right. Electronegativity, the ability of an atom to attract bonding electrons to itself when forming compounds, increases from left to right and decreases from top to bottom. Finally is the metallic character of an element, being how similar it is to metals in their characteristics, which decreases from left to right and increases from top to bottom. Chapter 5. Chemical bonding. For an atom to be stable, it must have a noble gas configuration, that is, having a full outer valence shell, being 2 for the first shell, or typically 8 for shells 2 and on. Of course, most atoms that aren't noble gases lack this, being every group except group 8, or group 18 if you're going with the complete set. They can achieve this state via either transferring electrons between them in ionic bonding or sharing electrons in covalent bonding. Ionic bonding. An easy example of ionic bonding is that of sodium chloride, in which the sodium has 1 valence electron, whereas chlorine has 7. Thus, sodium gives that 1 valence electron to the chlorine, giving them both full outer shell. This causes sodium to become a positively charged cation and chlorine an anion because the electron carries an electrical charge. This causes electrostatic attraction between the two ions, bonding them in the compound of sodium chloride. The formula is written as the two reactants being added together, with the product being the compound symbol. Ionic bonding and the periodic table. Atoms lose or gain electrons depending on how many valence electrons they have. As we saw in the example with sodium and chlorine, and as we also said before, the number of valence electrons an atom has is based on the group of its element. This means that only low and high groups often form ionic bonds, such as group 1 and 2, or group 16 and 17, whereas other groups may use covalent bonding, which we'll get into in a sec. Naming ionic compounds. The positive ion keeps its name and the negative ion gets the "ide" suffix, hence sodium chloride, or magnesium oxide. Also, elements have variable valencies such as copper, iron, or lead. For these, you have to put the Roman numerals in brackets next to them to specify. What we've looked at so far are monatomic ions, meaning it is an ion of one atom. However, there are also polyatomic ions, being their own sort of compounds with positive and negative charges, which act essentially the same as our monatomic ions, just this time being written in brackets in a chemical symbol for the ionic compound they participate in. Covalent bonding, being bonds formed by sharing valence electrons between atoms. For example, when we see chlorine gas, it is in molecules of 2 chlorine atoms. This is because they have a valence shell of 7. Thus, they share 1 electron of each of their valence electrons to share, and both have 8 valence electrons each, giving us the chemical symbol Cl2, written like this in the form of electron dot structure. Covalent molecular substances are simple covalent molecules. We also have the molecular formula, which tells us how many of each atom are in each molecule. Within the context of the periodic table, both elements must need to gain electrons in order to attain noble gas configuration. Therefore, meaning the number of covalent bonds an atom has is the number of electrons it needs to gain. We can deduce how many of each atom is needed in a covalent molecule by comparing how many electrons are needed to fill either shell. For example, chlorine only needs 1 more electron as it is a valence shell of 7, whereas carbon needs 4. Thus, for them to bond, we need a molecule of 4 chlorine and 1 carbon atoms. Now, some pairs of elements can form either a covalent or ionic bond. So, how do we decide? We look at electronegativity. To be ionic, one element must have greater electronegativity than the other, or if they're covalent, electronegativity must be relatively equal. But we can sidestep this by just looking at valency, whether they need to gain or lose electrons to have noble gas configuration. That is, if one must gain and the other must lose, it is ionic. If they both must gain, then it's covalent. Naming covalent binary compounds. Step 1. Decide which element comes first and second, as the first is the one with lower electronegativity than the second. Step 2. Use a normal name for the first element and then add the "ide" suffix for the second. Step 3. Use the number of each atom in a molecule as the prefix. But don't use mono for 1 as a prefix on the first, just leave it bare. For example, we get carbon monoxide or dinitrogen pentoxide. Properties of ionic and covalent molecular substances. Ionic substances have a high melting point when solid, are hard due to strong electrostatic force, brittle because electrostatic forces can be flipped to repel if disturbed, and as solids can't conduct electricity because the ionic lattice is too tight for the atoms to move towards the charged electrode, but can conduct as liquids because they are broken down to have more space to move. Covalent molecular substances are weak and have low boiling points because of their weaker intermolecular forces, which we'll get into later, and can't conduct electricity as they are a neutral species because of their lack of ions. Covalent network solids. They are solids where covalent bonding extends indefinitely to form a crystal in a lattice, kinda like ionic substances. They have properties of a high melting point because covalent bonds are very strong, and there is no need for intermolecular forces because it's like everything is one big molecule. But they can't conduct electricity because there are no ions, meaning that there are no free-moving electrons. Metallic bonding. Metallic structure bonding is an orderly 3D array of positive ions held together by delocalized electrons via electrostatic force between the positive ions and negative electrons. Delocalized electrons are electrons which belong to no atoms, breaking away from the valence shell to form the positive ions which form a metallic structure. Most of metals' properties, such as hardness, malleability, and conductivity, are due to this. Chapter 6: Intermolecular Forces and Allotropy. Intermolecular forces are those which bond molecules into substances, the strength of which defines properties such as a substance's melting and boiling points. Polar covalent bonds and polar molecules. Pairs of identical atoms in a covalent molecule, such as chlorine gas, share electrons evenly. But when they're not identical, the electrons spend more time closer to one nucleus than the other, and obviously this is due to the electronegativity of the atoms present in the molecule. In hydrogen chloride, chlorine has slightly higher electronegativity than hydrogen, meaning the electrons are closer to it. This is notated by the delta symbol, meaning slightly charged one way or the other. Polar covalent bonds are those which have charges of opposite polarity within the molecule, and dipole is when these opposite charges are equal. Polar molecules have this. However, in polyatomic molecules, polar covalent bonds don't always form a dipole because the charges can be cancelled out by one another. This is called a non-polar or flat molecule. Predicting the shapes of molecules. Let's introduce the valence shell electron pair repulsion theory. This proposes that electron pairs around an atom in a molecule space themselves apart equally to be as far apart as possible due to the electrostatic repulsion of like charges. When we have two bonds, they are on opposite sides of the central atom. When we have three bonds, they're evenly spaced with 120 degrees between them in an equilateral triangle. When we have four bonds, each of the attached atoms form corners of a tetrahedron with the central atom at the center of it. We can also have lone pairs of electrons, that is, electron pairs that aren't used for bonding, however they're still kept at an equal distance from the other electron pairs. Hence, ammonia forms a tetrahedron with the central atom at the top vertex. With that out of the way, we can now look at different types of intermolecular forces. First up, we got dipole-dipole forces. That is, dipole covalent molecules have a positive and negative end, so they attach at ends via electrostatic forces. Next, we have dispersion forces, which occur between non-polar molecules, in which the electrons are in continual motion, and when you have a billion individual molecules in a substance, the clock is right more than twice a day. That is, eventually, each molecule rotates to perform a dipole-dipole-alike force. However, it is significantly weaker as it is an irregular occurrence between molecules, individual molecules that is. Its strength is hence dictated by the number of electrons in a molecule. The larger the molecule, the larger the intermolecular force. But that still doesn't match up to the dipole-dipole force. We then have hydrogen bonding, in which hydrogen atoms within a molecule can bond to more than one oxygen, nitrogen, or fluorine atom, as they have the highest electronegativity. These forces are significantly stronger than dipole-dipole forces, since hydrogen is literally just a proton. Therefore, the distance between molecules is significantly closer. And finally, we're on to our last subchapter, allotropy. This is the existence of two or more physically distinct forms of an element within the same physical state. For example, carbon as a solid can be diamond, but could also be graphite, both made from the same element but have physically distinct properties. These various forms are called allotropes. The difference between the allotropes in our example of carbon is the number of carbon atoms bonded to one another. In graphite, each atom has 5 bonds, whereas in diamond, each atom has 4 bonds. Their respective structures are also different. Diamond is in a 3-dimensional crystal, whereas graphite is in layers of hexagonal 2D lattices. Or sulfur has rhombic and monoclinic sulfur, which have a circular structure of 8 atoms, whereas plastic sulfur has the structure of a single file chain, giving the two forms distinctly different properties. There we go, a whole module of chemistry in one video. For those of you here for an exam, good luck, and for those of you here on leisure, please seek out help. But to everyone who watched this video, thanks for watching.